Today we'll be working on 7.11 to 7.14. This is all about solubility equilibrium. So we'll be taking the concepts of equilibrium, of general equilibrium that we've learned, and we're going to apply this to solubility equilibria. So next class, you will have a little bit more time to finish up your lab, and I'm going to ask you to do your CER individually on your reading and reflection document. So let's get started with our notes for today. So our outcomes are listed here. We're going to be looking at the solubility of a salt, and we're going to be relating that to KSP, the common ion effect, pH, and we'll talk a little bit about free energy, the energy changes that occur when a salt dissolves in water. So why is solubility an important phenomenon? Why do we study it? So some examples, salt and sugar dissolve to flavor foods. Calcium sulfate is more soluble in hot water than in cold water. So we see that whenever your water boiler heats and cools down, that we start to get some of that boiler scale from calcium sulfate. Your teeth contain hydroxyapatite, which reacts with acids from food. Fluoride replaces the hydroxide ion to form fluorapatite, which are both less soluble in acids. And another example would be barium sulfate. Barium sulfate is ingested to improve the clarity of X-rays of the digestive tract. Barium ion is actually very highly toxic, but since the solubility of barium sulfate is so low, nearly none of that is formed. So even though you're ingesting a toxic compound, it doesn't do any harm and just passes right through your system. So how is dissolving an equilibrium process? So if we have a solid like silver chloride, and we take that solid and we put it into water, it's going to dissociate to give me silver ions and chloride ions in a 1-to-1 ratio. So silver chloride is what we call a slightly soluble salt. So it's not all going to dissolve. We'll still have a chunk of solid silver chloride sitting in the bottom of the beaker. But as some of that silver and chloride ion starts to dissolve, the concentration of those ions will begin to increase. And this makes it more likely for those ions to collide together and reform the solid. So in this diagram here, you see that you have some arrows that are representing the dissolving and some arrows that represent precipitation, the formation of the solid from those ions. So this process reaches an equilibrium where the amount of AgCl, Ag+, and Cl- all remain constant. So we can describe that equilibrium using what's called the solubility product constant. So the way that we write this is the same as we would for any other equilibrium expression, except because my reactant is a solid, we would exclude that from our equilibrium expression here. So we write K with an SP to represent solubility product, and it's going to be the concentration of the ions raised to whatever coefficient they have in the balanced equation. And again, we see no reactants here because my reactant is a solid. So the value of KSP tells me how soluble a given compound is in water at a specific temperature. So it is just a equilibrium constant. Whenever we say solubility product, we're looking for the equilibrium constant. And whenever we ask for things like solubility, we are looking for the equilibrium concentration of those ions once they have dissolved. So looking at the dissolving of calcium fluoride here, my equilibrium expression is going to include the concentration of calcium times the concentration of fluoride, which is going to be squared because of the 2 coefficient that we see in the equation. So how is KSP used to determine the solubility of a salt? So we just discussed that the solubility is how much dissolves, how much of it is present when we reach our equilibrium. So in this case, we're looking at copper 2 iodate. So if you take copper 2 iodate and add it to some water, it's going to break apart and give you copper ions, and it's going to give us 2 of these iodate ions here. So we know the value of KSP. We want to calculate its solubility. In other words, how much of it will really dissolve here. So my KSP expression is going to look like this. Again, note that the 2 has become a square in my KSP expression. So we're basically trying to figure out how much copper and how much iodate are going to be present at equilibrium when I drop this salt into water. So we are going to initially start out, we're only going to include the copper and the iodate because those are the only things that appear in my KSP expression. Now initially, we don't have any of those ions present when we first put the solid into the water. So we know that there's going to be some change. We're going to gain some amount of copper ion and twice that amount of iodate ion. So my equilibrium conditions here are just going to be X and 2X. So plugging that into my KSP expression, I end up with KSP is equal to X times 2X squared. So 2X squared is going to give me my 4X squared times X gives me 4X cubed. So we can do a little bit of math here. We'll need to divide by 4 and take a cubic root. But we get the concentration here of this compound at 25 degrees Celsius. So this is how much copper, and twice that value would give us the amount of iodate that actually has formed. So we would have 3.3 times 10 to the negative 3 for copper, and then 6.6 times 10 to the negative 3 for iodate. Copper 1 bromide has a measured solubility of 2 times 10 to the negative 4 moles per liter. We want to calculate the KSP value. So we're kind of going in the opposite direction. In the previous problem, we were given KSP and we were asked to find solubility. Here, we're given solubility and we're asked to find KSP. So let's start with writing an equation for the dissolving of copper 1 bromide. So since this is copper 1 bromide and bromide has a -1 charge, my compound is just CuBr, and I'm going to get copper and bromide ion in a 1-to-1 ratio here. Now I know the solubility of this compound, which is basically telling me how much Cu and how much Br are going to be present at equilibrium. So in my Rice chart, I'm again only going to include my Cu and Br because CuBr solid is not going to appear in the equilibrium expression. And initially, I know that there is none of those ions present. I know that it's going to change by 2 times 10 to the negative 4. So since these are both in a 1-to-1 ratio, the change for both of these is the same. So KSP is going to be equal to the concentration of Cu plus times Br minus. And I know the value of that, so I can plug that in here. And this gives me 4 times 10 to the negative 8 for my KSP value. So KSP lets us figure out how much of a salt is going to actually dissolve and be present in the water at equilibrium. So how does KSP relate to the solubility guidelines? So compounds that have a large KSP are what we would call soluble. So these are going to be things that include your group 1 ions, ammonium, nitrate. The compounds that are highly soluble are going to have a large KSP value. It's kind of like when we have a chemical reaction and it has a large K, we say the reaction goes to completion. Here, when KSP is large, it's telling us that all of that salt is going to dissolve. Now, when we have a small KSP, that gives us our slightly soluble and insoluble salts. So the words slightly soluble and insoluble are actually interchangeable. They both just mean that when I add that salt, that not all of it is going to dissolve, only a small fraction of it will. Now you can compare the KSP of one salt to the KSP of another salt, but only if they form the same number of ions. Otherwise, your KSP expressions are different. So if we look at these two equations here, and we were to solve for our KSP expression using a Rice chart, you see that we get 4x cubed versus x squared. So because these expressions are different, I can't really compare the KSP of lead chloride to silver chloride and make any meaningful comparison here. I can't say lead chloride is more soluble than silver chloride because I can't directly compare these because they form a different number of ions. So what is the common ion effect? So this describes an ion's effect on the solubility equilibrium of a salt. So, for example, the solubility of NaCl is much higher in pure water than it would be in a solution of KCl. So if we look at this example here, if I put silver chloride into some salt water, the silver chloride solid is going to be much less soluble than it would be in pure water. And that's because the presence of the common ion, Cl-, in the solution is going to limit the ability of the NaCl to dissolve. So the presence of a common ion will reduce the solubility of a salt. So here we have the KSP for silver sulfate, and we want to calculate the solubility of solid Ag2SO4 in each of the following. So first we're going to look at it in water. Then we're going to look at it in silver nitrate. Now, silver nitrate has the common ion silver, so we're expecting our answer for solubility to be lower in B than it is in A. So let's take a look at finding the solubility of this salt in water. So I'm going to go ahead and start by making my Rice chart. And we're looking at the dissolving of silver sulfate in water. So if I have solid silver sulfate, it's going to dissolve and form silver plus 1 ion. We're going to get 2 of those. And we're going to get some sulfate minus 2 ion as well. So in my KSP expression, I'm going to have the concentration of silver squared times the concentration of the sulfate ion. So in my Rice chart, I'm only going to include my silver and my sulfate. So initially in the water, we don't have any of these ions formed. So in order to get to equilibrium, I'm going to gain some amount, twice the amount of silver as sulfate because of the reaction stoichiometry. So at equilibrium, my concentration of silver will be X, and my concentration of sulfate, my concentration of silver will be 2X, and my concentration of sulfate will be X. So I'm going to go ahead and plug this into my KSP expression. So it's going to be equal to 2X squared times X. So when I solve this, I'm going to get 1.2 times 10 to the negative 5 is equal to, I'll have 4x squared times x. And so when I multiply these together and combine them, I end up with 1.2 times 10 to the negative 5 is equal to 4x cubed. So I'm going to need to divide by 4. And then I'm going to need to take my cubed root here. But when I solve this, I get that x is equal to 0.0144. So this means that the concentration of silver is twice that amount. So that's going to give me 0.0288 molar. And the concentration of sulfate is just equal to X. So the concentration of sulfate here would be 0.0144 molar. So this gives us the solubility of these two compounds in pure water. So now we want to do a similar calculation. This time we're going to do this in a solution of silver nitrate. So once again, I'm going to write my same reaction here. So silver sulfate solid is going to dissociate to give me 2 silver ions and 1 sulfate ion. And my KSP expression is still the same. It's the concentration of silver squared times the concentration of sulfate. Okay, now we are making this solution in some 0.1 molar AgNO3. So if I have 0.10 molar AgNO3, when that dissociates, it's going to give me 0.10 molar Ag and 0.10 molar NO3. Now, silver nitrate is a soluble salt, so I don't need a KSP expression to know how much silver and how much nitrate are going to be present at equilibrium. I know, because it is a soluble salt, that all of my silver nitrate will break apart into silver and nitrate. So I'm going to go ahead and make my Rice chart here. Now, my reaction, again, I'm going to include just the things that are in my KSP expression. So that would be silver ion and sulfate ion. Now, in pure water, the initial concentration of both of these is 0. But we don't have pure water here. I am starting with this much, 0.10 molar Ag present in my solution already. And I don't have any sulfate. So I'm still going to have a change here. I'm going to gain 2x here, and I'm going to gain x here. We know that we have to gain on the product side because there's no sulfate. So at equilibrium, my expression here is going to be 0.10 plus 2x, and then we also have x. So I'm going to go ahead and plug this into my KSP expression. So 1.2 times 10 to the negative 5 is going to be equal to 0.10 plus 2x, and that guy is squared, times x. So this is going to give us a pretty nasty equation to try to deal with here, because we're going to end up with the quadratic equation and we'll have to solve it. So the way around this is to use my k is small shortcut. So if k is sufficiently small, it means that 0.1 plus 2x is pretty much just going to be equal to 0.1. X is going to be a really small number, so if I add it, it's not really going to give me much of a change. So that leaves us with this situation. We have 1.2 times 10 to negative 5. That is going to be my KSP value. And that is equal to 0.10 times x. Excuse me, 0.10 squared times x. So whenever we solve this, we're going to need to divide and then get our answer here. So my answer that I come up with here is that x is equal to 0.0012. So now that we've solved for the value of x here, we can go ahead and put that into our equilibrium expression here. So for silver, it is 0.10 plus 2x. So that's going to end up with 0.1024 molarity for silver. And then for sulfate, it's just going to be x. So we end up with this guy. We see that the solubility of silver is going to be of silver sulfate is less in the presence of silver nitrate than it is in pure water. So the silver that is already present in the water is going to limit the solubility of the silver sulfate. So we can compare the values that we got, and we see that it is much lower in this experiment. How does pH impact the solubility of a salt? So when calcium fluoride is added to water, we're going to form some calcium and 2 fluoride ions. That's going to be their ratio because of the stoichiometry. Now, if we add some H plus from an acid to this solution, we're going to form HF, which is a weak acid. What that means is that the F here is being stored in the form of HF. So HF is a weak acid. It's not going to dissolve very much at equilibrium. So the concentration of fluoride ion decreases. Once HF is formed, this weak acid will not dissociate, and it will effectively store the F- in the form of HF. Why does adding an acid have an impact on the dissolving of calcium fluoride, but none on the dissolving of silver chloride? So F- is what we call a weak base, and it will react and form HF, a weak acid, which is not going to dissociate. If H and Cl were to form a compound, HCl is a strong acid, so it would dissolve completely. So this is going to have an impact on the solubility of calcium fluoride, but not on the dissolving of silver chloride. So what factors influence the ability of a salt to dissolve in water? We have to look at 2 things. First, enthalpy changes. These are changes in the heat content of the system. So in order to dissolve a salt, we have to break interactions and form new interactions. So we're going to have some change in the energy or the heat content of the system. We also have disorder changes. So these are changes in the arrangement of matter within the system. Whenever you go from a solid salt to an aqueous salt, those particles are arranged differently. So we also have some changes in the order or the arrangement of the system. What values of enthalpy are favorable for dissolving? So there are energy changes that occur in soluble salts. So first, energy has to be absorbed to break interactions. So the interactions that have to break here are the intermolecular forces between water molecules and the ionic bond, the ion-to-ion attractions present in the salt. And then we're going to release energy as we form ion dipole attractions between the water and salt. So energy absorbed is going to give me a negative delta H, and energy energy absorbed is positive delta H, energy released is negative delta H. So depending on the relative sizes of these changes, that'll dictate whether delta H is positive or negative. So when we have a negative delta H, this is going to be favorable. This is going to be an exothermic reaction. If delta H is positive, this is unfavorable and endothermic. So in order for something to dissolve endothermically, that heat needs to be available to be absorbed. And if this heat is not available, it creates a barrier to the reaction. So what values of entropy, delta S, are favorable? So entropy is a measure of the dispersal of energy and matter. So as salts dissociate into ions, the entropy increases. There's more ways to arrange salt particles in water than there is in just solid salt. So a positive delta S is going to be favorable. Breaking attractions increases entropy, and so this doesn't cause any barrier to the reaction. But if my delta S is negative, this is unfavorable. Forming attractions is decreasing entropy, and this is going to be a barrier that's going to prevent the reaction. So this leads us to an expression called Gibbs free energy. So free energy is the energy that is available to do the work of dissolving that solid salt into water. So the Gibbs free energy equation combines H and delta S terms into one equation here. So delta G equals delta H minus T delta S. When we have a positive delta G, it means the reaction is thermodynamically unfavorable. So this is what applies to our insoluble and / slightly soluble salts. A negative delta G is going to be thermodynamically favorable. This is going to apply to our soluble salts. So what I'd like you to do next is to write a summary of your notes. You can talk about writing KSP expressions, solving for solubility and KSP, the impact of a common ion on solubility, impact of pH on solubility, conditions that are favorable to dissolving, and Gibbs free energy. You have reflection questions for 7.11 to 7.14. So for homework, I want you to complete the summary of your notes and answer the reflection questions, which will be turned in next time. And I want you to complete topic questions 4.11 to 7.11 to 7.14 and your progress check reflection questions. Watch videos and add to your notes from class, and we will have Mastery Check 7 next class, which of course means that your progress reflection and your topic questions will be due.